Welcome back to the Deep Dive. I'm your host, and today we are doing something a little distinct from our usual format.
Yeah, that's right.
Usually, we take a stack of articles and research papers and we just we talk about them, we explore. But today, we are going to play a role,
We are.
or rather, we are going to simulate a very specific, very high pressure professional environment.
That's right. We aren't just observers today. We are putting you, the listener, right into the driver's seat.
But not the driver's seat of a car.
No. We are putting you in the driver's seat of a high-stakes boardroom presentation.
Okay, so I want you to close your eyes, assuming, of course, you aren't currently operating heavy machinery, and imagine you are wearing a very sharp, probably very expensive suit. You are a senior technical strategy consultant at one of the world's most prestigious automotive consulting firms. You know, the kind of place where you charge by the minute and probably use words like synergy, completely unironically.
But today, there is absolutely no room for fluff. You have just walked into a boardroom at the headquarters of a major global OEM. You can feel the air conditioning humming that low, expensive hum.
The coffee on the sideboard is probably lukewarm.
It always is. And sitting around this huge mahogany table are your clients.
And let's be crystal clear about who these clients are. This isn't the marketing team. This isn't, HR.
No.
You are staring down the chief engineer of powertrains, the head of global charging infrastructure, and the lead automotive electronic architects.
These are the people who literally built the internal combustion era. Their names are on patents for fuel injection systems and transmissions, and now they are tasked with building the electric future.
And they are probably a little skeptical, a little defensive.
They don't need the basics. They definitely know how a lithium-ion cell works. They know the difference between AC and DC. What they're facing is, well, it's a crisis of complexity. They are looking at the next 6 years, from right now, 2024, all the way to 2030, and they just see a fragmented landscape of changing standards, massive power requirements, and frankly, software nightmares.
Exactly. They are drowning in technical noise. So they've hired us, or more accurately, they've hired you to cut through that noise. Your mission, should you choose to accept it, is to deliver a global EV charging technologist strategy that clears the fog.
And we're going to give them the executive summary right up front. The core thesis we're presenting today is a fundamental shift in mindset.
Okay.
For the last decade, the entire industry has viewed charging as simply energy refilling. It was a gas station model. You put the nozzle in, fluid goes in, you leave.
Simple, very transactional.
But that era is over. It's done. The new thesis is that the vehicle is becoming a hub for bidirectional energy and data interaction.
Okay, that's a mouthful. Break that down.
It's no longer just a tank to be filled. It's a node. An intelligent node in a massive distributed network. It can send power back, it can send data, it can make financial transactions on its own.
So how do we structure this report? If we just start throwing facts and specs at these engineers, they're going to, eat us alive. We need a framework.
We do. And we are going to use a classic McKinsey-style approach. We're going strictly top-down, and we're adhering religiously to the MECE principle.
MECE. Okay, spell that out. MECE.
Mutually exclusive, collectively exhaustive.
The gold standard for strategic consulting.
It really is. It means we are going to break this huge, messy problem down into distinct buckets that do not overlap with each other.
So mutually exclusive.
Right. But when you put those buckets together, they cover absolutely everything. No gaps. Collectively exhaustive.
It's an elegant way to tackle chaos. Okay, so let's outline our buckets. What are the 3 pillars of this strategic report?
Pillar 1 is the power dimension. This is the big iron, the physics fight. We're going to analyze the physical movement of energy, specifically this massive leap to megawatt charging, or MCS, for the commercial sector.
The heavy artillery.
The heaviest. Then, pillar 2 is the protocol dimension. This is the software and the logic layer. The brains of the operation.
Exactly. We have to navigate what we're calling the war of standards. You've got NACS versus CCS versus CHOUG, and we'll explain how to use software abstraction to survive that chaos.
So how to make sure the car speaks the right language, no matter where in the world it wakes up?
Precisely. And finally, pillar 3 is the ecosystem dimension. This is where finance meets physics. We'll get into the weeds of the trust economy, the insane complexity of plug and charge, and the future of vehicle-to-grid, or VTG.
All right, consultant. The CEO is checking his watch. The chief engineer has his arms crossed. Let's open the slide deck. Section 1, the power dimension.
We're starting with the commercial vehicle revolution.
Okay, so the client throws the first curveball. The head of infrastructure leans back in his chair and says, look, We have 350 kilowatt fast chargers. We've spent millions, maybe billions deploying them. They charge a sedan in 20 minutes. Why isn't that enough? Why are you telling us we need to invent a whole new system called MCS? And that's a perfectly fair question, but it also reveals that they're still thinking like car drivers, not like logistics operators.
Okay.
The answer lies in a concept we call zero time loss.
Zero time loss. That definitely sounds like something a logistics manager dreams about at night.
It is the holy grail, and it's not driven by technology, it's driven by regulation. Let's look at the source data, specifically the European Union regulations for truck drivers.
Okay, lay it out for us.
Legally, a truck driver in the EU must take a mandatory 45-minute break after every 4.5 hours of driving.
And that's a hard constraint.
It's a hard legal constraint. The vehicle's tachograph is recording every single second. You cannot drive 4 hours and 31 minutes. You stop, or you and your company get hit with massive fines.
Right. So for 45 minutes, that truck is parked. The driver's getting a coffee, stretching their legs. That asset, that very expensive truck, is idle.
In the diesel world, that's fine. Refueling takes, what, 10, maybe 15 minutes? The remaining 30, 35 minutes of that break is pure rest.
Yeah.
The truck is ready to go long before the driver is. But in the electric world, if you use current CCS technology, even the best 350 kilowatt or 500 kilowatt chargers, you physically cannot replenish the 4.5 hours of driving range within that 45-minute window.
You just can't get the electrons in fast enough. The pipe is too small.
The pipe is way too small. You end up sitting there for 60, maybe 90 minutes, depending on the battery size. And that extra time, the time the truck is waiting for a charge after the driver is legally rested and ready to go, that is dead money.
So it's a direct operational loss.
It is. The data indicates that sticking with current fast charging causes a 7.4% time loss in logistics operations when you compare it directly to diesel.
And 7.4% might sound small to a layperson, but in the world of logistics.
In logistics, margins are razor thin. A 7.4% efficiency hit is the difference between a profitable fleet and a bankrupt one. It's a non-starter. You cannot go to a company like Maersk or DHL and ask them to accept that penalty.
So the engineering target for MCS isn't some arbitrary number pulled out of a hat. It's calculated. It's designed specifically so we can charge the truck fast enough to fit perfectly inside that mandatory 45-minute lunch break.
Precisely. That is the zero time loss model. And to achieve that, we need to pump energy at a rate that CCS simply cannot touch. We are talking about target parameters of up to 3.75 megawatts.
Okay, 3.75 megawatts. Let's just pause on that number for a second because it's abstract. Help us visualize what that kind of power actually looks like.
Well, a standard home in the U.S., when the air conditioning and the oven are on, might pull maybe 3 to 5 kilowatts at its absolute peak.
Okay.
So 3.75 megawatts, which is 3,750 kilowatts, is roughly the power consumption of a small town.
Yeah.
We're talking about 800 to 1,000 homes worth of electricity.
All flowing through a single cable into a single vehicle.
In 45 minutes.
That is just, it's mind-boggling. And technically, how are we achieving that? What are the volts and amps we're working with?
The voltage is high. The target is 1,250 volts. But honestly, voltage isn't the really scary part. We know how to insulate for high voltage. The number that should make every engineer in that room sit up straight is the current. We are pushing 3,000 amperes.
3,000 amps. Okay, for context again, a standard household wall socket in North America is rated for 15 amps.
Exactly. So just imagine 200 of those wall sockets short-circuiting at the exact same time, and you're the one holding the wire.
Right. That brings us to the technical deep dive portion of this section, because when you push 3,000 amps through anything, you have a problem. And that problem is called I²R loss.
Physics. It's just physics. Resistance creates heat. And at this level of current, it creates massive, dangerous amounts of heat. This is where we bring in the insights from AVL, one of the top powertrain consultancies in the world. They identified this heat challenge as the single biggest engineering barrier to making MCS a reality.
So the obvious naive question is, can't we just make the copper cable thicker, lower the resistance?
You could, but at 3,000 amps, to keep it from overheating with passive air cooling, the cable would need to be the diameter of a fire hydrant.
Oh, wow.
It would weigh hundreds of pounds. No human driver could possibly lift it or maneuver it into the socket. It's not feasible. So we have to keep the copper relatively thin and manage the heat aggressively.
And how aggressive are we talking here?
We're talking about active liquid cooling. Everywhere. We're not just cooling the charging station cabinet anymore. The MCS architecture requires active liquid cooling for the inlet. That is the actual socket on the truck itself.
Wait, hold on. You're saying the socket on the truck has coolant lines, like a radiator running directly to it?
Yes. The metal pins that make contact, the ones carrying the 3,000 amps, are hollowed out, and a cooling fluid is pumped through them constantly during the charging session.
That's incredible.
And it doesn't stop there. The high-voltage cables running from that socket to the battery pack inside the truck, those are liquid-cooled too. They're basically flexible insulated coolant hoses with a copper core. If you don't cool them, they will melt their own insulation in minutes.
So that adds a whole new layer of complexity to the vehicle build. You have a cooling circuit just for the charging system.
You do. It adds cost, weight, and potential points of failure. But there's another thermal bottleneck that AVL highlighted in their research, and it's one that catches a lot of engineers off guard. It's the battery itself.
What do you mean by that?
You can't just dump 3,000 amps into a single battery terminal post. It's like, as we said, trying to drink from a fire hose. You literally vaporize the terminal.
Right, so you have to split the current. This is the power distribution unit, or PDU strategy you mentioned?
Correct. The moment that power enters the truck, the PDU has to intelligently split it into multiple parallel paths. Maybe it sends 600 amps to this battery pack, 600 to another, and so on. These battery packs are often distributed around the truck's frame.
But even with that splitting, the losses inside the battery must be significant.
They are. AVL did a fascinating loss analysis on this, and this is a key slide for our client. You have to show them where the energy is actually going.
Okay, run us through the numbers.
It's really interesting. You'd think most of the loss, the heat, is generated in the charging cable. But actually, the vast majority of energy loss, about 7.27%, happens inside the individual battery cells. It's due to their internal chemical resistance. The battery itself fights back against being charged that quickly.
Okay, so 7.27% of 3 megawatts is, let me do the math, that's over 200 kilowatts.
Over 200 kilowatts of heat.
Being generated inside the battery packs. That's not an oven, that's a forge.
Exactly, which is why the battery's own thermal management system has to be incredibly robust. But here's the kicker. That cooling system itself takes a lot of power to run.
Ah, the parasitic load.
Right. The pumps, the fans, the compressors, all told, they consume about 1.86% of the total energy being transferred.
So, let me get this straight. For every $100 of electricity I'm buying to put into my truck, nearly $2 is immediately burned just to run the air conditioning to keep the system from exploding.
That's a perfect way to put it. That is the unavoidable cost of doing business in this zero-time loss world.
Okay, so we've established it's a thermal nightmare on the vehicle side. Now let's pivot to the other side of the equation, the grid.
The big, big problem.
If I'm a fleet operator and I build a depot for, say, 20 of these electric trucks, and let's say they all need to charge during the same few hours overnight, that's a 60, maybe 70 megawatt peak demand.
Or more.
The local utility company isn't going to send me a Christmas card. They're going to shut me down or charge me demand fees that are so high they effectively bankrupt my company.
100%. You cannot just hook a gigawatt-class charging park directly to the medium voltage grid without some kind of buffer. It would be catastrophic for local grid stability.
And this is where the Nefton project comes in.
Yes. This was a critical research initiative in Europe, involving players like AVL, and MAN Truck and Bus. They demonstrated the absolute necessity of buffer batteries at the charging site.
So explain the modular matrix concept to the client. How does this work?
Imagine a large shipping container, or maybe several, sitting next to your row of chargers. These containers are packed with stationary batteries. Could be new, could be second life EV batteries.
Okay.
This container sips power from the grid 24 hours a day, slowly, gently, at a low, constant rate that the grid barely even notices. It's filling up like a cistern or a water tower.
So the grid just sees this low, flat line of consumption. Very predictable, very easy to manage.
Exactly. But then, when a truck pulls up for its mandatory 45-minute break, the charging station doesn't pull from the grid, it pulls from the container. The container dumps all that stored energy into the truck at 3 megawatts.
So the grid doesn't feel that massive, spiky demand at all. The container takes the hit.
It completely decouples the truck's demand from the grid supply. This is the only way to make these depots financially and technically viable. But, of course, there is a catch.
There's always a catch.
For this to make any financial sense, the power electronics, the inverters and converters moving energy between the grid, the buffer, and the truck must be incredibly efficient.
What kind of efficiency are we talking about?
The target set by the Nefton project is greater than 98%. round-trip efficiency.
98%.
If you're running at, say, 95% efficiency, you might think that's pretty good. But at these power levels, that 3% difference means you're generating so much waste heat inside that container that you now need a massive dedicated AC unit just to cool your buffer battery.
And that cooling system costs money to buy and money to run.
And it completely destroys your total cost of ownership, your TCO. So efficiency is king.
So, to summarize our strategic takeaway number 1 for the power dimension, you must adopt MCS for the business case to work for commercial fleets. But MCS isn't just a bigger plug. It's a vehicle-level thermal management nightmare that almost certainly requires on-site stationary storage to be viable from a grid perspective.
Correct. And our advice to the client has to be, don't wait. The standards bodies, Charson, ISO, and the IEC are on track to finalize the MCS standards by 2025. If your engineering teams aren't prototyping this right now, you are already behind the curve.
All right, that's a powerful and slightly terrifying opening. Let's move to the second pillar of our report, the protocol dimension.
Right. This is where we leave the physics lab with all the melting copper, and we enter the much cleaner but maybe more confusing world of international diplomacy.
The war of standards.
War of standards.
Let's paint the map for the client because it's a real mess out there.
It is deeply fragmented, and we can break it down into 3 major economic and regulatory blocks. First, North America. Here, the war is effectively over. Tesla won. We are seeing a massive industry-wide migration to NACS, the North American Charging Standard, which has now been formalized by the SAE as J3400.
It's not just a Tesla thing anymore?
Not at all. Ford, GM, Rivian, Volvo, Polestar, almost everyone has announced they're adopting the NACS port for their vehicles sold in North America starting in 2025. The dominoes have all fallen.
So in the US, Canada, and Mexico, the Tesla plug is the future?
Yes. But then you get on a plane and you cross the Atlantic to Europe, and it's a completely different world. They are strictly regulated to use CCS2, the combined charging system.
And that's mandated by law?
It is mandated by EU law. It's part of their alternative fuels infrastructure regulation. You cannot sell a car with an NACS port in Germany or France. It has to be CCS2.
Okay, so 2 continents, 2 different plugs. Now let's look east.
Right. Looking at Asia, specifically China and Japan, you have another set of standards. China uses GBT, and Japan famously developed CHAdeMO.
The 2 giants of the Asian auto market.
But they recognized this fragmentation was a problem. So they've been collaborating for years on a new unified super standard called Chaoji.
Chaoji, what does that mean?
It literally means super or ultra in Mandarin. And it's designed for ultra-high power, up to 900 kilowatts. So it's very similar in ambition to MCS, but potentially for passenger cars, too.
Okay, so we have NACS in America, CCS2 in Europe, and Chaoji rising in Asia. Here is the strategic risk for our client in that boardroom. They want to build one global car platform.
Of course. That's the holy grail of automotive manufacturing.
They want to design the chassis and the core electronics once, and then sell that car in New York, Berlin, and Shanghai with minimal changes. But they can't put 3 different charging sockets on the fender.
Well, the physical socket itself is actually the easy part of the problem. That's just swapping out a plastic and metal assembly on the production line based on where the car is being shipped.
So what's the hard part?
The real nightmare is the logic, the brain, the software. Each of these standards, NACS, CCS, GBT, they all speak a slightly different dialect of the charging language. The handshake protocols, the data packets, the timing requirements, the error codes, they're all subtly different.
So if you hard code your charging logic for CCS, it's just not going to understand what an NACS charger is saying to it.
It'll be gibberish. It won't work. So what's our recommendation? How do we solve this puzzle?
Tell us.
We look to the insights from software specialists like Electrobit. Their core strategy is architecture decoupling.
Decoupling. Break that down for the engineers in the room.
We need to build hardware-agnostic software. I like to use the printer analogy. Think of your laptop. You can plug in a printer from HP or Canon or Epson. Your word processor doesn't care which one it is.
Right. The app just says print.
Exactly. The operating system handles the low-level driver, it does the translation, and the application just works. We need to do the same thing for charging.
So the car's central brain, the part that manages the battery, shouldn't care if it's plugged into a Tesla supercharger in California or a European Ionity station in Italy.
Precisely. The software stack must be designed with a hardware abstraction layer. It needs to support dynamic switching between all the protocols. It needs to speak ISO 15118, which is the language of CCS. It needs to speak DIN 70121, which is the older, simpler dialect of CCS. It needs to speak GBT 27930 for China and CHAdeMO for Japan.
So the core application logic, charge the battery to 80% remains the same, while a lower-level driver handles the specific translation for whatever plug is currently attached.
That's the architecture. And where the software actually lives is also changing. In the olden days, there was a specific little black box called the EVCZ, the Electric Vehicle Communication Controller, a dedicated ECU.
A standalone unit?
Yes, that's old school now. The industry is moving rapidly towards zonal architecture.
Oh, okay.
We're getting rid of the dozens, sometimes hundreds of little ECUs and consolidating their functions into a few powerful central computers or zonal controllers.
Right.
So charging control is migrating. It's becoming a software function running within the classic AUTOSAR environment on one of these powerful zonal controllers.
So charging is essentially becoming an app on the car's main server.
That's a great way to think about it. This saves a huge amount of weight and wiring, which is critical in an EV. But it also raises the stakes for software stability and security. If your charging app crashes, your whole car might need a reboot.
Now, speaking of software standards, there is one specific ISO standard that keeps coming up in all our research. It seems to be the key to everything. ISO 1518-20.
The one ring to rule them all.
We need to be very, very clear with the client here. There is an older version of this standard, ISO 15118-2. A lot of current EVs use it. Why are we telling them to skip it entirely and jump straight to the new one?
Because ISO 15118-2 is a dead end. It was designed for the last generation of EVs. If you want your vehicle platform to be competitive in 2026, 2027, and beyond, you must move directly to ISO 15118-20. Investing any more time or money in NATI 2 is just technical debt.
Okay, that's a bold claim. So what does NEMA 20 give us that NATI 2 doesn't? Why is it so important?
It enables what I call the holy trinity of future charging features. 3 critical things the old standard can't do.
Okay, what's the first?
First is bidirectional power transfer, BPT. This is the foundation for vehicle-to-grid, V2G, and vehicle-to-home, V2H. If you want to sell power back to the grid from your car's battery, or power your house during a blackout, you need -20.
The old standard couldn't do that.
Not really. It had a very rudimentary, limited form, but -20 has the rich data fields you need to properly negotiate prices, grid status, and power flow directions. It turns the car into a real grid asset.
Okay, that's essential for the ecosystem pillar we're going to talk about later. What's number 2?
Second, automated connection devices,
Yeah.
ACD. This is some of the more futuristic stuff. We're talking about those robotic pantographs that drop down from the ceiling to charge electric buses, or robotic arms that will come out and plug your car in automatically in a parking garage.
True autonomous charging.
Exactly. ISO 15118-20 has native support for that robotic handshake and alignment process. The old standard has no concept of it.
And the third part of the trinity.
Megawatt charging, MCS. This brings us full circle back to our first pillar. You simply cannot run a 3,000 amp MCS station on the old protocol. The data exchange requirements, the safety interlocks, the thermal monitoring data, it all requires the bandwidth and structure of ISO 15118-20.
So let me recap for the client. If you want your future vehicle platform to support V2G or robotic charging or megawatt speeds for your commercial vehicles, you have no choice. It has to be ISO 15118-20.
It's the only path forward. But there is a very significant hardware implication here. This isn't just a free software update.
Ah, okay. The other shoe drops.
Oh, absolutely. The new NAC 220 standard brings a massive security upgrade. It mandates the use of TLS 1.3.
Transport layer security, that's the same encryption that protects our online banking, right?
Yes, but specifically version 1.3, which is the latest and greatest, it gets rid of a lot of old insecure cryptographic algorithms, and as a result, it is computationally very heavy. It requires robust crypto suites algorithms with names like CHA20 and ED448.
Those sound like dance moves from the future, but I assume they are just really complex math.
Extremely complex math. And here is the billion-dollar trap for our client. If they're hardware architects 3 years ago trying to save $5 per car, picked a cheap, low-power microcontroller for the charging ECU.
It might not be strong enough to do the math in time.
Exactly. It will choke. It won't be able to perform the encrypted handshake in the milliseconds required by the standard.
Yeah.
The charger will time out, and the car just won't charge.
So the strategic warning for the C-suite is, check your silicon. You need to make sure your hardware roadmap includes a powerful hardware security module, HSM, that is capable of running TLS 1.3 efficiently.
That is a critical piece of advice. Don't let a cost-cutting decision from 3 years ago cripple your entire next-generation platform.
Wow, okay. That is a fantastic point. Let's move to the third and final pillar of our report, The ecosystem dimension. This is where we stop talking so much about volts and code, and we start talking about value and trust.
That's right. The fundamental shift here is from charging to energy transaction. The car is becoming a wallet on wheels.
And the key technology enabling this magical future is plug and charge, or PNC.
Ideally, PNC is magic. It's the experience Tesla owners have had for years. You pull up to a supercharger, you plug in, and that's it.
It just works.
It just works. The car talks to the charger, it securely verifies your identity, it processes the payment against your account, and it starts charging. No apps, no credit cards, no RFID fobs to fumble with.
But according to the insights from our sources at software firms like KPIT, making that magic happen for a multi-brand open network is incredibly difficult. They call it a hidden web of complexity.
It absolutely is.
Yeah.
And it's because the number of actors involved explodes. In the old gas station model, the transaction was simple. It was between you and the pump.
Yeah.
And maybe your bank, 2 or 3 parties.
Mm-hmm.
In the PNC model, for a single session to work, you have the OEM, who made the car. You have the CPO, the charge point operator, who owns the physical charger. You have the MO, the mobility operator, who you have your payment contract with. And you have the DSO, the distribution system operator, who manages the local power grid.
It's a committee meeting just to turn on the power.
And they all have to trust each other instantly, in milliseconds. That chain of trust is built on a technology called PKI, public key infrastructure.
Digital certificates, like the little padlock in your web browser.
Exactly like that, but for cars. The car has a unique, unforgeable digital birth certificate installed at the factory. The charging station has one. Your utility contract has one. When you plug in, they all have to exchange these certificates in a cryptographic dance to prove they are who they say they are.
The complexity isn't just checking them, is it? It's managing them over the life of the car.
That's the real nightmare. Provisioning, installing, updating, and most importantly, revoking these certificates. What happens when a certificate expires? Or worse, what happens if a car is stolen?
That's a great question.
That's the scenario that keeps security architects up at night. You need a system for revocation. You need to publish what's called a CRL, a certificate revocation list. If a car is stolen, you need to blacklist its digital certificate so the thief can't drive around getting free electricity on your account.
Okay, so you put the stolen car's ID on the list. Simple enough.
It sounds simple, but how do you get that updated list to 500,000 charging stations scattered around the world instantly? Many of those stations are in underground garages with spotty cellular connections.
So a charger might be working off an old, outdated list.
And if it has an old list, it will happily authorize the stolen car because it doesn't know the certificate has been revoked. It's a massive distributed IT challenge.
And it seems like ISO 151-1820 adds even more complexity here. I'm seeing something in the notes called multi-contract handling.
It does. But this is actually a really cool feature for users, especially in the commercial space. Let me explain the use case.
Please do.
Imagine you drive an electric delivery van for a company like Amazon. When you're at the depot overnight, you plug the van in, and the charging cost is automatically billed to Amazon. That's your corporate contract.
Right. Makes sense.
But then on the weekend, your boss says you can take the van home to move some furniture. You plug it into your charger in your driveway. You should pay for that electricity, not Amazon.
Or maybe I'm on a long-distance delivery route, and I need to use a public charger that isn't part of the Amazon network.
Exactly. The vehicle needs to be able to hold multiple digital contracts simultaneously. It's like having a personal Visa card and a corporate Amex card in your Apple Wallet.
And when you plug in, the car and the charger have to be smart enough to negotiate and pick the right one.
Yes. The car says, here's my location. Here are the network IDs of the charger. Okay, based on my internal rules, I should use the personal contract for this session. And all of this has to happen automatically, seamlessly, in the background.
The user shouldn't have to dig through 3 layers of menus on the infotainment screen every time they charge.
It has to be invisible. Implementing that decision tree logic, the whose money are we spending algorithm, is a major software challenge for the OEMs.
And finally, under this ecosystem pillar, we have the really big one, V2G.
Vehicle to grid. This changes everything. It fundamentally alters the legal and financial relationship between the car and the world. The car is no longer just a consumer of energy.
It's a supplier. It's a power plant on wheels.
It is, and that requires a whole new level of intelligence.
Yeah.
It requires precise synchronization with the grid's EMS, energy management system. The car needs to know the real-time price of energy, which might change every 5 minutes. It needs to know if the grid is stressed and needs support. It needs to have a trading strategy. It needs to make a decision. Do I charge my battery right now while electricity is cheap, or do I sell 20 kilowatt hours back to the grid right now and make a profit because it's peak demand?
So the software engineer working on the charging stack isn't just writing charging control code anymore. They're writing automated trading algorithms.
Effectively, yes. The car becomes an autonomous financial agent trading on the energy market.
Okay, we've covered the three dimensions: power, protocol, and ecosystem. The sheer complexity is, well, it's overwhelming. I can imagine the executives around that mahogany table are looking a bit pale right now.
I'm sure they are.
The chief engineer, the one who's been silent this whole time, leans forward and asks the ultimate strategy question. He says, "Look, we are a massive global automaker. We have thousands of very smart software engineers. Should we build this entire charging software stack ourselves? Should we own the code from top to bottom?"
This is the classic buy versus make decision. It's a question every executive faces. And based on the data from our sources like Electrobit and KPIT, our recommendation to them is emphatic and unequivocal. No, do not build it. Buy it.
That is a very strong, very direct stance. Why are you so certain?
Two main reasons: speed and maintenance. Let's start with speed. The data shows that integrating a commercial, pre-validated software stack from a specialized vendor like a KPIT or an Electrobit saves approximately 40% of development time compared to building it from scratch.
40%. In the automotive world, that is the difference between launching the car on time and missing the entire model year.
It's a huge schedule advantage. But honestly, the bigger, more strategic issue is maintenance. It's a monster.
What do you mean?
These standards, ISO 1FE11820, NACS, OCPP, the security protocols, they are not static. They are living documents. They are constantly being updated, patched, and revised by international committees.
So the goalposts are always moving.
Always. If you build your own stack, you have to dedicate a permanent team of your best engineers just to watch the standards bodies, attend the conferences, and then rewrite your code every 6 months to stay compliant.
You essentially become a standards compliance company, not a car company.
That is the perfect summary. You're burning headcount on non-differentiating work. If you buy the stack, the vendor does all of that for you. You are essentially buying regulatory compliance as a service.
So the strategy is to outsource the plumbing, let someone else worry about the pipes, and you can focus on building a great car and a great user experience on top of it.
Precisely. No customer has ever bought a car because it has a really elegant implementation of the D96-70121 handshake protocol. They buy it because it charges reliably and easily every single time.
Okay, but what about the risk of interoperability? If I buy a commercial stack, does that guarantee my car will work flawlessly with every single one of the thousands of different chargers out there?
No, absolutely not. Nothing is guaranteed. The ecosystem is still too young and too fractured for that.
So what's the solution?
The solution is a robust and continuous validation strategy. You can't just test in your own lab against a few reference chargers. You need to use third-party validation suites and participate in industry-wide testing events, like the Turin Testivals.
Festival?
Yeah, it's a real thing. It's where all the car makers and charger manufacturers get together in a giant parking lot for a week and just try to plug everything into everything else to find the bugs.
A giant hackathon for EVs.
Essentially, yes. And crucially, our client must ensure their back-end cloud management system complies with the latest version of OCPP, which is 2.0.1.
OCPP, that's the Open Charge Point Protocol.
Right, that's the language the charging station uses to talk to its cloud management system. You can have a perfect conversation between the car and the charger using ISO 15118, but if the station's backend speaks old, clunky version of OCPP, the chain breaks. The digital certificate data gets lost in translation, and plug and charge fails.
It's an incredibly fragile chain of communication.
And you are only as strong as your weakest link. Every single node in that chain has to be speaking the same modern dialect.
Before we wrap up the recommendations, I want to circle back to safety one last time. It feels important. We talked about the terrifying amount of heat in MCS. What is the specific strategic directive there?
Our recommendation is that you must implement ISO 26262 ACL level thermal monitoring.
ACL. That's the Automotive Safety Integrity Level. That's the heavy-duty functional safety standard. That's the standard we use for things like brakes and airbags and steering.
Correct. You cannot treat the temperature sensors in an MCS inlet like the thermostat in your living room. They must be treated as safety-critical inputs with redundancy and fault detection.
So what happens if a sensor detects a problem?
If the system detects that the contact resistance is spiking, which means a hotspot is forming, it must derate. It must cut the power immediately.
How fast is immediately?
We are talking milliseconds. If your software takes even a second to think about it and get around to cutting the current, you have already melted the connector pin. Thermal runaway at 3 megawatts is not a bug. It is a very, very fast explosion.
That is a sobering thought to leave them with. All right, the coffee is definitely cold. The hour is up. Let's summarize our strategic report for the client. Give me the final high-level bullet points for the CEO.
Okay, here's the roadmap for 2024 to 2030.
1.
On power. You must adopt MCS immediately for your commercial vehicle platforms. The zero-time loss business case absolutely demands it. But you have to budget for active inlet cooling on the vehicle and strongly consider stationary buffer storage at depots to handle the grid impact.
Got it. Number 2.
2. On protocol, don't fight the hardware war. Abstract the plug. Win the software war. Use architecture decoupling to build a global platform. And standardize all new development on ISO 151-1820 now to future-proof your products for VTG and MCS.
And the third takeaway.
3. On the ecosystem. Invest heavily in your PKI and back-end certificate management capabilities. And don't try to be a hero. Buy a commercial software stack to handle the brutal complexity of plug and charge. Do not waste your valuable internal engineering resources building commodity plumbing.
That's a clear, actionable strategy. And finally, as we always do, let's leave the client and our listeners with a provocation. A final thought on where this is all really going.
As we were analyzing all this data, one realization just stood out above everything else. We are building commercial vehicles that can push and pull 3 megawatts of power from the grid. Now, think about a logistics depot. If you have a parking lot with just 100 of these trucks parked overnight, that is a 300 megawatt controllable electrical node.
300 megawatts. That is not a parking lot. That is a medium-sized gas turbine power plant.
Exactly. The automotive industry is accidentally, almost as a side effect of electrification, becoming the largest distributed utility company in the world. Wow. So the final question for every engineer and executive listening is this. Are you ready to be energy traders? Because the grid is going to ask you to trade. Your fleet customers are going to expect you to trade to lower their costs. The car isn't just a transportation asset anymore. It is a currency in the global energy market.
The car as currency. I love that. Perfect place to end. Consultant, thank you for that incredible deep dive. And to our listeners, our client for the day, we hope this roadmap helps you navigate the chaos of the coming decade.
Good luck. You're going to need it.
We'll see you on the next deep dive.